Alrighty, so today we're going to be having a look at sketching tan, and the first thing that I want to talk about is the fact, let's talk some tan, because tan's quite an interesting function. So we've been talking about the definition of tan for a long time as just being the sine over cosine, which is very much true, but one thing that I haven't really spoken too much about is if we use our unit circle, and I take this angle theta, right? It's going to have a point up here, cos x, cos theta, sine theta. I think we're all pretty happy with that at this point. However, the interesting part is, what's the slope of this line? Well, we define slope, or gradient, as rise over run, which just happens to be the sine coordinate over the cosine coordinate. But that's also how we define tan. So when we talk about tan, what we're really saying is, when we draw the unit circle, what's the slope of the line? When tan equals 1, what that's saying is that your rise over run is 1. So it adds a little bit more sensibleness, because all of a sudden we don't have to think as much, right? Because if I see that tan is running along the x-axis, well, what's the slope? It's 0. When tan is running up the y-axis, what's the size? Well, it's undefined. We don't have any run. It's only rise. So it's really important for us to just kind of get a visual intuition. It also tells us another thing, which is why if this line here has a slope of, let's call it m, then if I were to turn 180 degrees or pi degrees, well, that line pointing down would have the exact same slope. It's pointing the wrong way, but its slope is actually the same, because we always measure rise over run going forwards. So the rise over run here would actually match the rise over run there. So just a really important point to bring out visually, what is tan actually talking about? It's actually talking about the slope of this line. Well, that gives us some really easy ways, right? We're going to be 0 when we're on the axis, so at 0 and pi, and well then 2 pi dot 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 tan is going to be equal to 0. But then we can think about these ones up here, right? What we also know is that when we're directly vertical, what's the behavior going to look like? Well, we're going to get pi, and then also when we're down, so that would be pi on 2, sorry, and we get 3 pi on 2, and then if we add, so then 5 pi on 2, then tan is going to be undefined. So that's just some important background before we start sketching. Now the basic shape of tan is this one. It starts at, well, look, at 0, the line is flat, so it starts at 0, and then it has another 0 at pi, and another 0 at 2 pi. And then halfway in between, at pi on 2 and 3 pi on 2, it has no value. It is undefined here, and it is undefined here. So then all we need to do is work out what happens in between each of the asymptotes. So let's look in between pi on 2 and 3 pi on 2 to work out what goes on. So, after pi on 2, what happens? Well, pi on 2 is here, so therefore after pi on 2 would be something like this, and 3 pi on 2 would be something like this, and we know in the middle it will be 0. So we ask, well, what's the slope of this line that I'm doing in yellow? Well, it's negative, isn't it? You can quite clearly see that it's negative. And in fact, when it's quite close to pi on 2, it's very steep, so it will be very, very negative. Similarly, when we look at this line here, you can see that that's a positive line, right? It's going up. The slope of that line is positive. So we can imagine that as it gets really, really close to 3 pi on 2, that the line is going to get steeper and steeper and steeper, meaning very, very high gradient. Alrighty, so that kind of tells us that coming this way, it sort of does this. It's coming from the negative, and then it goes up towards the positive. And so we get this shape. You can double check it on your calculator, but this is the shape we get. And it repeats, because, as we said before, tan is a repeating shape. So this is our basic shape. We can dilate it, we can do all of the usual translations. The major difference is that when we calculate the period using that b value, it's just pi over the absolute value of b. So the period changes, and so the period could be, well, the period's pi from here to here, but it's also pi from the first asymptote to the second asymptote. So just be mindful of that. Alrighty, so let's have a look at actually solving one.